and he's going to talk about the tree-wise series. I think you want to say something about the theory and examples.
Okay, so thank you. So I'm going to, my title is Tree Index Series, Theory and Examples. And today I want mainly to explain two things. So the first one, let me start there. So the first one is the fact that there's a natural way, if you're given, if you're given an opera to build a group and it's really a natural construction, so I will take some time to explain this construction. And the second point I want to make today is that I want to apply this construction to one specific operad. And this specific operad is called the Privy operad. And the resulting group can be described as a group of tree indexed series. And I will say more things about elements in this, some elements in this group. So, well, for me, let me just say a little bit more about those 2 points. So, for me, the operads will always be what is called algebraic operads. There will be operads in the category of vector spaces. And mostly, well, there will be always symmetric operads, although it's not really important, but I will stick to the symmetric case. And what I want to do is to define a functor. This guy there should be a functor from the category of operads to the category of groups. And the group which we obtain in that way, they resemble a group of formal power series for the composition. So it's more precisely, they resembles the set of invertible power series of a composition. And in fact, on this vector space of formal power series, you do not only have the composition, but of course you have the addition and the multiplication. And so this will be a general. Okay, thanks. This will be a general fact that on those groups we have there will be more than just the composition. There will be also other operations and the compatibility between composition and product, but all here we also have analogs in the general case. So it's in some sense that this construction is trying to define something like P formal power series and study their properties. Now, this is a very general thing for all operads, and why is it interesting to do that for Prelly operad? Because the Prelly operad has a basis indexed by rooted trees, and so the result will be a group on tree index series. And in fact, there have been, since the 60s, there has been a use of tree index series in numerical analysis, and then they really work with this object without knowing that it comes from an operad. They use this tree index series, and so so maybe I should give some names. So this is used in numerical analysis, and more precisely in the study of Runge-Kutta method. Runge-Kutta methods are methods for approximate solution of ordinary differential equations. And there are many such methods. It's essentially one can choose a square matrix and it gives such a method. And so around the 60s, John Butcher has found a way to encode this Runge-Kutta method using a tree-indexed series. And so these series are known as Butcher series in the community of numerical analysis. What would be a typical example? So a typical example would be something like, well, let me draw it and I will comment. So so this is an infinite sum of trees. So the trees are rooted trees. So I'm always going to draw the root at the bottom. So the trees are growing up. And I first write all the trees with one vertex, and all the trees with two vertices, and all the trees with three, and so on. So this is well, it's like a power series, except that the indices are not integers, but the indices are trees, and each index has a coefficient, which can be taken, for instance, to be a rational number. So my aim is to try to explain why this guy, people in numerical analysis have been using that, why it fits in the general theory of operads, and another aim will be to try to present examples of series like that, which will be something like analogues of the exponential power series or analogues of the logarithm power series. And so let me know, I will start by explaining the general theory. So let P be a symmetric operad in the monoidal category of vector spaces over Q of a tensor product. So P is a collection of P of n, which is a vector space with an action of a symmetric group Sn. I have the identity, the unit of the operad in P of 1, and I have composition maps, which I will denote by gamma. For some reasons that will appear later in the talk, I need to make more assumptions. So I need to assume that the P0 is just the zero vector space. There's no zero array operation. And P of 1 is just a one-dimensional vector space, which is spanned by the unit. Okay. So now I think you have seen that already, but let me recall the free algebra of free P algebra on a space, on a vector space W. So it's, well, I'm not going to explain why it is a P algebra, I'm just recalling the definition briefly. So it's, I will denote this by P of W, well, some kind of abusing notation because there's nothing to do with P of n, W is a vector space, and it's a direct sum over n greater than 1 of P of n tensor product over W tensor power n, and it's a tensor product over the symmetric group, which means that we have to quotient mod out by the relation that x sigma tensor y is equal to x tensor sigma y for every sigma in the symmetric group. Okay, so this space is a graded space and it's a P algebra, and in fact it's a free one, so it satisfies a universal property which is as follows. So if you have a linear map from a vector space V to so this is just a vector space, and A is a P algebra. Then there exists, it should be called W. So there exists a unique morphism of P algebra which extends the map F, which makes the following diagram commutative. So it's W to A, and then there's a map from W to P of W, and this is F here in this comment. So this inclusion comes from the fact that I have a unit in P of 1, so this gives a map from W to P of W, such that commutes. Okay. So this construction, if you apply it to either the commutative or the associative operad, you get well-known things. So for com, how many m's to come? So com of W is just the direct sum of, well, the com of n is a trivial representation. So when we take the product, we just obtain the symmetric pole of the vector space. So it's a polynomial ring without the degree 0 part. And for associative, okay, I don't know. Well, the degree n part of the associative operad is just a regular representation, so it's a unit for the tensor product over Sn, and so we get just the sum direct of the pole of a vector space. And this is the usual tensor algebra without the degree 0 component. Okay, so now I want to use this but only for a dimension 1 space of generators. So I consider W to be just the field, the base field, and okay, so what we get is a bit more simpler because it's just a direct sum of what is usually denoted by P to n with index Sn, which is the space of co-invariance of the action of a symmetry group. Co-invariance. We just mean that we mod out by x sigma is the same as x for all sigma in the symmetry group. Okay, so if in that case, of course, we for com and for us, it's the same thing. Both are isomorphic to polynomial rings without the degree 0. So we don't see any difference between associative and commutative there. And so still there's the universal property, which can be rephrased a little bit by saying that whatever a P algebra and an element A, small a, there exists a unique morphism of P algebra, which goes from so P of Q to A, and which maps the, okay, so let me, I will use the bracket to denote the class in the co-invariant. So here, this guy is this space is a quotient of the P of n, so I'm going this bracket symbol to denote the image in the co-invariant. And so here I have the image of the unit of the, well, yeah, the unit of the operad, so it should go to the chosen element. Okay, I'm doing all this because I will use this to define this group I want to talk about. Okay, so in fact, I'm almost done. So this property is universal, so it holds whatever the P algebra we choose. So we can take as a P algebra this space itself. So it says that whatever element in P of Q, there exists a map in P of Q to itself, which sends the class of the unit to A. Okay, let's call this map phi A. And what I say is that this map should be thought of as the map of substitution by A. It's a substitution operator. So let's consider for a moment just the case of P equals CRAM. So what does this mean? It means that if I if I take this, so it means that I have a map from polynomials in one variable to polynomials in one variables. And it is defined uniquely as a morphism of commutative algebra, which sends x to some polynomial, Q polynomial, a chosen polynomial. So this is phi Q. So what is this doing? You just take, if you take a polynomial here, and it's a morphism of commutative algebra. So it's every product of every pair of x will be mapped to a pair of Q, and then you take linear combination. So in fact, it's the evaluation of R on the polynomial Q. Okay, this is. I think it's clear, but of course I'm so used to that.
Can you do the exact same thing without switching to the co-invariants first?
Well, you need something which is an algebra. So I don't think, well, I don't really need the symmetric group action. I could do that with non-symmetric operads, in which case there's no need to go to the co-invariants. That's one answer, maybe. Otherwise, for symmetric operads, I don't think we can do that without taking the co-invariants. Anyway, so, okay, so now a question for you. So what's the composite map of phi Q and phi Q prime? So phi Q means I replace the arguments of a polynomial by Q. So I first replace the argument by Q prime, and then I replace by Q. So it's the same as replacing the argument of a polynomial by Q prime of Q. So it's the composite of the polynomials, except it's in the other sense. It's in the other order. Here is the composite. composition of these two polynomials. And so we do exactly the same thing. So we go back to the case, the general case of an operad, and we do the same thing. So I claim that if I now take those phi, which are, yes, I should have. I should have given a name here, so it's phi.
It's over there, no phi A. It's on the top.
Oh, yeah, okay, so it's. Okay, so now I claim that if I take A, B in P of Q, then there exists a unit C such that phi of A, phi of B is phi of A, phi of B is phi of C. So this left-hand side is just the composition of linear maps. So of course, it's well defined. And there, we see that all those substitution operators, they are closed under composition. So there's a new element, and of course I will define the composition of B and A to be C. So it's just the same principle, except that we don't do that with polynomials, but with elements in 3 P algebras and 1 generator. So what can we? I'm going to explain how we find this C, how it is defined concretely. But first, just from this result, we can see that this thing is associative. Because, of course, it inherits the associativity of the composition of linear maps. Well, of course, there's a unit. So the class of I is a unit. Because if you look at what's phi of I, it's the identity of P of Q, so it's the unit for this side. And so we have, we have a monoid with unit. And it's a non-linear monoid. It's not an algebra at all. That's an important point. It's linear. So it's linear, but only on the left. Okay, if you think of the composition of two polynomials, of course it's linear on the exterior argument, but not in the thing we compose inside. So, and there's more than that. There's also the fact that okay, this is maybe less clear, but I don't want really to. So it's. The composition is left distributive. Distributive with respect to the P algebra structure. P algebra operations. So if you think again of just in the polynomial case, if you take f times g, and in which you put q of x, then it's f of q of x times j of q of x. So here, instead of having just a commutative product on the 3 P algebra and 1 generator, we have the products of the algebras, which can be many. Okay, so this is some kind of non-linear monoid, which looks like the composition of polynomials. Sorry. And I want to explain now okay, how this C can be found. How it is defined. And it goes as follows. You first recall that we are, there's a discussion, so we are in the free algebra is the direction of the co-invariant, and there's this quotient map. Just going to the co-invariant. So if I want to compute this composition, I take A, B, two elements in this sum. I pick representatives. Of these things. And now, well, the composition is the class of. I need one more notation, so I'm decomposing A as a sum of homogeneous components. So yeah, it's a finite sum. And here I'm doing the sum of n greater than 1 of the composition of an, n, b, 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 n times. So this sum is finite, and so this sum is also finite, and so we take the image in the co-invariance and we obtain an element which is there. Okay, one has to prove that this does not depend on the representatives. That's something that needs to be proved to show that it works. But otherwise, you see that we are just using the composition map of the operad. And maybe we also use the action of a symmetry group. But, well, it's a rather simple recipe how to build this. So if you look at that, what it says is that in fact this thing is given by the simultaneous insertion of B in every argument of A. It's like we are using the composition, but all the same arguments repeated. Okay, so it's rather easy that, well, from this thing, once we have checked that it does what it's supposed to be, that it does not depend on choices and it's associative and so on, then it gives a functor from, well, I will write operads for those operads I consider now, and two monoids. Okay, so far I have not speak about the inverses of the element. So it's just a monoid with a unit.
Is it not this composition automatically a group? It seems.
No, because well, you have 0 inside that. 0 is an element and it has no inverse. And there are, if you think in terms of power series with 0 constant terms, then they should have a non-zero degree 1 term. So it's something smaller. So I'm going to do that right now.
Because in the A1 you could have Cx and C should be there.
Okay, so yeah, so
usually one normalizes
of course,
x plus x squared plus
I promised to talk about groups, so it's I know I have to. So if you look at just invertible elements in this monoid, then there's not a lot of them. Just think of polynomials which would be invertible for the composition. There's just the affine polynomials with non-zero leading term. So in case of com, if you look at x, q of x, and invertible, P is invertible, we obtain just P equal AX plus B with A and C. So it's a very small group. So the group.
Will be
E of X.
No.
Oh, polynomial.
Invertible as a polynomial. We require that the inverse for composition is a polynomial. And it's not possible.
But I thought you had zero constant term.
There's no B, huh? You have no constant.
Oh, yeah. Okay. Yeah. Okay, well, yeah. Sure. Yeah. So it's very small group anyway. So what we have to do is to take a completion.
I was ahead of time. I was thinking about the series.
And we consider instead the P hat of Q, which is a completion of a free P algebra, which is just the product of the co-invariants. So on this thing, well, what we have done before is still true. Everything works fine because we were before in a graded situation, so we can just take the limit of the. We can define this operation even on infinite sum of elements, and it works just the same with all the same properties. And so in case of a what do you want to say? Okay, so this is now we can define a functor from operads to groups, and these groups will be a set of invertible in this completely free algebra on one generator. And what, so, yeah, so this is something like P formal power series. So we had before was just P polynomials in one variable. And it's very easy to be invertible. You just, so invertible means that if you write an element as a sum of homogeneous components, it just occurs that A1 is not 0. Once, yeah.
well, when you compute the inverse, you get a sum over decompositions of polygons, don't you? So where does that come out? How do you get that from P?
Well,
You get stash f, the faces number of states, faces stash f polytope
in
coming out of nowhere.
in the case of usual formal power series,
Why is that?
where does it come from? Well, I'm not sure I can really answer this question. The existence of an inverse is done by recursion, and so here it's the same process. We can define the inverse because we can proceed by induction.
You want to invert here for composition. I mean, you
But
want to step by step.
the form,
I know that, but
yeah, but the
naturally
formulas
the
for the
coefficients
inverse.
naturally involve something that's operatic in nature. So is there
It's explained in the book. We have a section.
It's explained in your book.
Yes, so it's like when you compose, when you substitute these guys, you get trees which are grafted one above each other. Then the coefficients they come from the.
Maybe one point of view is that
I can explain later.
yeah, we can apply this functorial construction to free operads, and then we can see the combinatorics of trees which appear.
Isn't there an explanation of this fact in a little article John Reloading? Was it about the associate?
So I think I've said what I wanted to say on the general theory in some way, and I want now to go to the specific examples. I have still a few words to say about the origin of this thing. So, in some sense, there's a paper by Kapranov and Manin, which is entitled something like Morita Theory for Operas, and in which they build, starting from an operad, they build some kind of, well, they built a graded Lie algebra, and even slightly more, and well, this Lie algebra is the Lie algebra of this group, so the idea is always, in some sense, they already have this, the Lie algebra of the group, and even the group they know about it. So it was in around 99. Then there are two different, in some sense, parallel approaches. So Pepijn, van der Laan, which is as the Watson. So his point of view was rather to consider algebras. Of course, what I've presented this theory using groups, but in fact these are group schemes. So they have an algebra of regular function, and we can, this is an algebra, and we can state all these things in the language of algebra. It's an equivalent, just another language for the same thing. Around 2002 or 3, I'm not quite sure. So I have done these things also in 2002 using groups. So I will not speak a lot about algebras in this talk today, but it's for some things it's useful to be able to talk about algebras and things like that. Okay, so now I'm going to the second part, okay. And I'm going to talk about the Lie opera and to apply this group construction to it. So first I have to recall the Lie opera.
The Lie, not the Lie.
Lie. So it was introduced in a paper with Muriel Vernet a long time ago, and sort of a long time ago. And so, okay, so I have to define the underlying vector space and the composition. So let me start with the underlying vector space. So it's a symmetric operad in the category of vector spaces. So it has a basis indexed by rooted trees on the set 1 up to n. So
Binary?
no.
No?
No. So if you want a formal definition, it's just a graph which is connected, simply connected, and with a distinguished vertex. So I can maybe just draw.
When you mean the leaves, as a label for the leaves,
No, it's a label for the vertices.
or for the vertices.
This is a set of vertices.
Maybe a bit
this
confusing
is
because
the
we've been drawing all these trees.
Yeah,
with
okay, so
operads.
maybe a word of warning is necessary here because you have seen many operas where the labels were on the leaves and composition was grafting. So here it's something completely different. There are trees, but the composition is not grafting and the labels are on vertices. I will explain the composition and you will see that it has nothing to do, well, it has not much to do with grafting. In some sense, it's an accident that the basis is given by trees. It could be a combinatorial object with a composition, but it is trees. And so, just to be sure,
So the A should be unhappy. If not.
So here would be an example. So I always draw the root at the bottom. So this is the root. And then we have, and this guy is just the same as this guy. There's no, we don't look at them. Well, I need to draw them in the plane of the board, but they are not intrinsically ordered. Okay, so it's a very classical result which is attributed to Cayley that the number of such trees is n to the power n minus 1, so this is the dimension of the nth component of product of n. And it grows quite fast. It's a sequence of numbers which is growing faster than the exponential, than the factorial. Okay, so I think now I'm going to the composition. Oh, not well. Maybe before I define the composition, maybe I should. Before I define the composition, it's an operad, so it has an associated notion of algebra. So there's a notion of Prilly algebra. And Prilly algebra we have seen already a few times in these meetings. So I'm going just to recall the axiom. So it's a vector space V, and on the vector space there's an operation, bilinear map, bilinear operation, which is denoted by a triangle, and which satisfies a maximum, which is just, if you take the difference between these two things, then it's the same as the same, but with Z and Y exchanged. Okay, so it's well, if you have never met that, it's an axiom, an operation which satisfies this property. And there are, in fact, it's interesting because there are many examples. Otherwise, so examples. Well, first example is maybe you take any associative algebra. Why it is so? Because in an associative algebra, the first line is 0 and the second line is 0, so they are equal. So it's already a lot of examples, but it's not really a true Prilly algebra. So if you want true ones, then there are two prototypical examples, which are first on the Hochschild chain complex. Cochain. So it's the direct sum of of V tensor M to V. We have seen an operation which is the sum of all possible insertion of one bilinear map into the other, and maybe with signs or without signs. And both variants give Prilly algebras.
That's not really the Hochschild cochain complex, right? That's just the endomorphism operator.
Yeah.
Because you're not using the multiplication in any way.
True.
Then if we take into account the multiplication, then we have a DG. If we take the differential into account, we have a DG from.
Yeah. Okay. This thing. Well, we can take any operad, in fact, there.
Yeah.
And we take the sum of all partial composition maps, and it's a Prilly product too. There's a big family of examples coming from operads in general. So, and this is an algebraic family of examples in some sense, and there's a geometric one, which is the space of vector fields on some affine space of dimension D. So I will need this example later, so I will present the details and explain why it is an example later in the talk. Okay, so there are examples of 3D algebra. It's not an artificial notion. It has appeared long before the operads. Now, okay, I've started to describe the operads and the operad freely, and remains to describe the composition.
Are you going to say what this structure is on vector fields?
What?
I'm going to explain later, but
Or you can do it later.
yeah.
In the formula to express the D bracket, you keep only half of the term.
That's one way to say it.
What was the definition of vector of
You derivate y with respect to x.
It's the covariant derivative.
Covariant derivative.
Yeah.
If you
Ground x and y.
if you
Yeah, X and Y.
if you
Yeah.
Yes.
Yeah.
Okay, so I'm rather lazy, so I prefer to describe the circular composition rather than the gamma. It will be easier to make the drawing, so I'm just describing the composition of one, so it's a partial one. So I just have to say partial composition.
X, Y, where you leave it.
I guess it's yeah, it's okay for you have, no, nobody has. See, okay, no. And it has a basis in days like trees, so I'm going to define a bilinear operation. So it's enough to this composition is bilinear, so it's enough to define on the basis. And so I have to take S and T, two rooted trees, and define what is S circle I T, where I is the vertex of S. So it's a sum of all possible ways. So it's a sum of the functions from incoming so implicitly I'm orienting the edges towards the root, so from top to bottom. So at every vertex there are some incoming edges and one outgoing edge. So here it's the sum of all map from the set of incoming vertices in the tree S at the vertex I to a set of vertices of T. And here it's an operation we do using S and F and T to create it's a rooted tree. And probably the best thing I can do to explain that is an example. Otherwise, well, an example is really easy to understand. So let's take S, which is 4, 2, 1, 3. And let's take T equals 5, 6, 7. Okay, I'm using the freedom to change the labels. Labels are not really important. So just make sure that the labels are all different. And what's the composition? Then simply you draw S. So let's say that the I is 2. So it's this vertex, and the composition is something like it looks like a bit like Feynman diagrams composition. So we put the whole tree T inside the vertex I. So let me draw something like a big vertex 2. And inside the tree T. Okay? Now I erase this vertex, and there are edges which are not happy because they are not connected any longer to something. So I have to decide what to do with the edges. So here there's the edge which was outgoing of I. So this one, we decide to glue it to the root of T. Okay, it's unique, and we glue it to the root of T. Sometimes it may not be there, but then we have nothing to do. And then there remains these edges there, which were exactly the incoming edges at vertex I. These two incoming edges there. And we have to decide a way to glue them on some of the vertices of T. So here we have 9 choices, because we have 3 choices for the left one, which can be glued either to the 3 vertices, and 3 choices for this one. So one choice would be this one. And the result of this composition is this choice plus the 8 other choices.
Including the one when the two edges confluent.
Yeah, they can go both to 7 or both to 6. So yeah, 3 times 3 choices for this one and 3 independent choices for this other edge. So it's just an example, but you see that I don't want to write all the terms. It's very tedious to do that by hand. And that was, well, that's one of the reasons why I have a computer program to do that for me, and I almost never do this calculation at all. I know that it works, and what should I say else? Oh, yeah, the unit. I have not forgotten the unit. So the unit of the operad is just well, there's not much choice. It's just the tree. It's just a vertex and no edge. Okay, so I think I have given a very short description of the pre-operad, and now I can apply this functor. To it, and what we obtain is either 3 index polynomials or 3 index series. So we take the pre-operad, and we take the free pre algebra on one-dimensional vector space, or its completion, and a set of invertibles inside. And so what does it look like? What does it mean to take the co-invariance on this vector space of label tree? It means to forget labels. So a typical element of Prelie of Q would be something like this tree plus 1/2 plus this tree plus 1/3 of this tree plus 4 times this tree. This is an analog of a polynomial in one variable. Because there's only one variable, there's no need to put anything into the vertices. And if you want a formal power series, then you just have to you can go on and you can add an infinite. You can just don't stop at some degree, but go on forever. Well, okay. So we have a group of 3 index series, and there's the unit of the group is just this tree, which is of course it's the co-invariant class of this unit there, which is general principle. And we can compute in this group because the product is just given by the gamma map of the Prelie operad. So if you want, I can make a small computation in this group, but I'm not sure it's really to make it concrete up to the bottom. So I can, for instance, compute. Okay, I've got a problem because this is not 0. This is the tree with one vertex, but this is not the composition either because I have too many sepals. So well, yeah.
Is your coefficient 4 over there?
Yeah.
Why is that?
Just random coefficients. It's just one.
Oh, I see. Oh, it's not that.
This is a random series. I'm going to speak. Yeah, no. Later there will be some.
1/690.
Yeah, it could be. No, well, no way. So let me compute just for. So this is the composition. So let me underline the circle because you know.
It's small. So
Yeah, it's a small circle, but small and not small. It's not easy to see. So okay, so we have to take representative, compute the gamma of the representative, and then take the co-invariance. So let's say that I have to take this synthetic classical representative. I don't know, I take 1, 2, like that. Now I have to separate according to the homogeneous degree. So I will. It's going. The result is going to be the class of of gamma 1, 1, 2. This guy inside every vertex of this guy, and then the class of gamma 1, 2. Well, 1, 2 twice. Okay, this is the unit of the opera, so it just gives back this tree. So here the class will be this tree. And here, well, one has to compute the composition, the Trelli opera. So it's a sum of all possible ways to put this one small there, this one small there, and to graft back the edges which are not happy. So the result, it can be done as the composition of two partial compositions. Well, you first compose this one here, and then you compose this one in the top vertex of the result is that this class there is the sum of two trees. Okay, so just
questions?
it's no, there's no question. It's a very small example just to illustrate how it works concretely if we want to. Of course, we could do the same for polynomials, but we don't do that when you compute the composition of two formal power series. You don't say that I'm going to distinguish every variable and then I compose once I have distinguished variables and then I forgot the variables. So it's when I do that, I do no longer do these steps. I go directly from here to here. This is just the technical way it's done, but once you get used to that, you don't need to really do that. I think I'm going to make a break now, and we will go on later.
I just want to mention that Michel Lazare long ago introduced a special case of operads which were called analyses, and they introduced exactly the same way series and groups corresponding to composition in this case. So I think it was done long ago. What he had in mind was to understand the Campbell-Hausdorff.
Yeah.
You have to count multiplicities there,
Last time.
which
Last
trees
time.
can occur in this case.
Sorry, could you repeat?
Do you have to use multiplicities? Say,
Um,
the way in which you can plug in.
That was my question.
No, it's well, once the trees are labeled, there's no longer any symmetry factor involved, so there's nothing complicated to do. Here, you see, I want to put this tree with two vertices in every vertex of that guy.
That's unique.
And I don't want to say I put this one here and this one. Well, there's no really multiplicities because every vertex as a different label, so we cannot be. There's no confusion possible. Right? Is this because of this thing?
Yeah, so there are only these two trees, the sum of these two trees without any coefficient.
Yeah, this can be done. This can be done in two steps, in some sense. So this guy is going to be plugged in the 1, and this guy is going to be plugged in the 2. So let me first plug this guy in the 2, and we need to shift the indices. So the result is that it's 1, 2, 3. Just putting this one, and then I have to put this one in the first place here. And so it means that I'm blowing up, and I have to relabel again. So it's 3, 4. And then I have to make the sum of all possible ways to glue back this edge. So there are just two possible ways to this one or to this one, just two terms. It's the rule for the composition of the opera. Okay.
What time do we have to come back? You choose. You're the master.
I don't know, quarter past. Quarter is okay?
Allez, perfect. Quarter. 3.